Hello everyone, welcome back to OnPrep, and today we are discussing about one of the important topic which is widely asked in the system design interview, which is ticketing system. Also, BookMyShow, which is used across India for booking the movie tickets. Similarly, TicketMaster is being used in other countries. Though today we are gonna focus on the movie ticket booking system, but this concept can be applied for any system where the inventory is limited. I mean, it could be a airline reservations generally in the peak seasons for festivals during Christmas, New Year, where there's a lot of concurrency, where a lot of people are booking the tickets in airlines. Similarly, in weekends, holidays, festivals, many people are trying to book the movie ticket at the same time. So we wanted to focus on the concurrency issue for this particular system, and more specifically, interview would be looking for you how you would handle the concurrency happens during multiple people are trying to book the same ticket. And as we mentioned in one of the previous videos, we will be going with the step-by-step approach, and I recommend 7-step approach for system design interview. If you have not watched my previous video, I would highly recommend you to first watch the video, which will help you to understand the format of the system design interview. So let's start with step 1, which is functional requirement. Functional requirement is the core functionalities of the system which it must support. For example, we wanted to build the system which has a feature for searching the movie ticket. As I have mentioned earlier, this can be extended to any event similar to movie, but we wanted to focus on the movie as part of this requirement. Search movie by its name, category or language, and many other parameters. View movie details and book tickets. So these are the 3 core features which we are trying to build. And as we go in detail, we will see what are the bottlenecks are there when there are thousands of people trying to search the movie by a search criteria, and other part of the system are like when many people are trying to book the tickets at the same time. That has another challenge. So these 2 sub problems of these topics are totally different, and we wanted to focus on the core functionality, core requirement of the system, and show our technical skills how we can scale our system based on this core functionality. Next is the non-functional requirement. While we start the discussion about the non-functional requirement, we would also like to mention about the out of scopes or the assumptions what we are making, which we do not want to focus as part of onboarding of the users. So we will assume that the users are already logged in into our system, the third-party payment gateways integrations, and how these movies are being added or removed into the theater. Probably we will touch upon this when we will discuss about the deep dive. You can make a note of here like your assumptions or out of the scope requirement. For saving the time, you can also discuss orally instead of spending your time on making a note of all those things, because these are the assumptions which interviewer are also not expecting you to elaborate. In step 2, when we are discussing about the non-functional requirement, we wanted to first start with the low latency of the system, which we wanted to propose for the search of the movie. What does that mean is we should have a specific SLA. When user types a word in the search bar, user should be able to see the list of all the movies belonging to that criteria within, let's say, 1 second or within 500 millisecond. So these are the qualities of the system which we wanted, and how do we solve this problem technically, that we wanted to discuss further. At this point of time, we are just making a note of it that we need this specific quality into the system. If we talk about the cap theorem here, we should specifically mention if we partition the data at this point of time we don't know whether we need to partition the data or not, but some kind of a intuition we wanted to give, that we are thinking a back of our mind about if we need to partition the data, we wanted to give the priority to consistency over availability. But instead of just throwing these jargons, we wanted to mention which specific use case where we wanted to prioritize consistency over availability. We must have the consistency on booking tickets. What does that mean is, if a user is trying to book a ticket, it's okay to have some delay, but we should have the consistency in the system for ticket booking. We do not want to prioritize the availability in this use case. That means that, let's say if customer is trying to book a ticket, we book it very quickly, and asynchronously in parallel we are trying to save into our database. But meanwhile, we send the confirmation to the user that your ticket is booked. Still, the record is not being created into the database. So this would be pretty fast, and we can update the records, database records into the system parallelly. But this is what we do not want, because ticket booking is something which user is looking at that point of time about the confirmation on the ticket. Let's say if the ticket is not booked, user can go and try booking other tickets or other movies into other theaters. So it's okay to have some delay here, but we need a consistency on booking. In the second use case for CAP theorem, where we wanted to prioritize availability over consistency, in this case we wanted to prioritize for searching movies. What does this mean is, when user is trying to search for a movie, after entering few keywords, user wanted to see the movie list of movies as fast as possible. It's okay if some admins are trying to add the movies in the backend parallelly, and that information is not available within that millisecond of time. So let's say at that specific time there are 10 movies exist in the database, and if user enters few keyword, those all 10 movies matches the criteria, but still users see the 9 movies in the list. User doesn't see the 10th movie in the list, because that point of time movies are being added into the database, and how this movie will be available to the user, there might be a multiple phases in between, and that's where we wanted to prioritize availability over consistency. Here you can understand, instead of just discussing about the CAP theorem in a generic term, we are discussing about the CAP theorem for these specific use cases. And in fact, these are the very key pointers which you should highlight in the interview to show your in-depth technical skills. And this is how you will be moving towards the scalable system, on making the choices of the databases which you would be required, or the caching which you will require. Also, you can discuss about the back of the envelope calculation. I would suggest you to get this clarified with the interviewer if he is looking for you to get the actual numbers here for the users who are using your system. For learning purpose, I am going through this step, but in actual real interview, I would suggest not to get into this in detail to spend much of your time. So let's start with 100 million daily active users we have, on which every user is searching for 10 times in a day. That will be equals to 100 into 10 to the power 6, which is 1 million, into 10. This is equals to 10 to the power 6, 7, 8, 9, and we do have approximately 10 to the power 5 seconds in a day, that is, which is equals to 10k. So now you can see we do have 10k request per second for search. Next, for ticket booking, we have 100 million users, and let's say 1% of it, which is 1 million user, are trying to book the tickets every day. We have these many seconds in a day, so which would be 10 to the power 6 divided by 10 to the power 5. That would be your 10 request per second you are getting for ticket booking. And if you need to consider the peak traffic, generally this when the movie is launched, and when the festival season, when the airlines has opened their ticket bookings, so generally in this kind of system the peak is very important. And probably if you consider the peak as 100 times peak here, then it would be something like 1,001k request per second you are getting for the ticket booking. These are the calculations for the search request and the booking request. And as you see by now, this hardly mean anything for this system design interview. You get the numbers for the search and for the ticket booking. You know from this is you need a distributed system, because a one server will not be able to book these many tickets in case of concurrency. And here if you, let's say, some having some SLAs of 500 millisecond, and if you are having a single node for serving these many requests per second, you might not be able to meet the SLA of 500 millisecond. That's why you would need multiple instances of this service or API for the search API and the booking API as well. So again, I have just mentioned here these details for your learning purpose, and if your interviewer is actually looking for you to get into these calculations. Similarly, for storage, how much storage do you need? So you are having 1 million tickets being booked every day, because of 100 million, 1% of the users, let's say, trying to book a ticket. So 1 million, and let's say each ticket size is 1 kilobyte, which would be 10 to the power 3 with a very high level numbers. So you will need to the power 9, which is 1 GB of data per day. If you are considering for year, again we have 365 days in a year. We generally take 400 days in a year for our easy calculations. And let's say if you're considering this for the next 10 years, so this into 1 GB of data, which is 10 to the power 9, this will be equivalent to 10 to the power 9, 10, 11, 12. 10 to the power 12 is the terabyte, and we have 4. So we need 4 terabyte of data to store the storage for tickets for 100 million or 1 million people are trying to book tickets every day for the next 10 years. So if you would see here, the data is also not very large. This is 4 terabyte that can easily fit into a single server. So do you really need to partition your data? Now you can think about the cap theorem, which we have discussed earlier. So as I have mentioned in my previous video, when you need to partition the data, there are two reasons. One is the data cannot fit into a single machine, or the number of requests are very high. So let's say if you are storing a 4 terabyte of data in one server and you get a search request or a booking request, you need to do the complete scan of these tables. Let's say you are scanning 1 terabyte of data in your table, in your search table or a booking table or getting a movie detail table. That's gonna take huge amount of time. So for this reason, probably you would require to partition the data, to split the data into a server which might have, like, let's say 10 GB of data. So instead of scanning a terabyte of data, you will be scanning in few gigabyte of data, and your performance would be much faster. So this is about the non-functional requirement, and I would suggest and highly recommend to not to get into these details. Just randomly suggest some numbers and get the buy-in from the interviewer that you are looking for the partitioning of the data that you will want to explain and get into detail when you discuss about the deep dive of the system, and that you have mentioned here with a very quick information that you are thinking about the cap while searching for a movie or while booking for a movie ticket. With that, let's get started with our step number 3, which is the schema design. This is the little tricky part where you do not have the complete picture about what all schema you would need in your system. So I would suggest you start with something simple here, that for your DB schema or core entities, you need a user. Now the user would have the name, ID, mobile or email address, etc. etc. Apart from user, you would need a movie. The movie would have again the ID, name, category, language. Let's say at this point of time you know only these two information. That is completely fine. And then you can say that as of now you can think about these two important entities and you wanted to jump into the API design. Probably you will come back here to add more core entities into the system. So let's get to the next step, which is API design. What kind of API do we need for searching a movie, getting to know the movie details and booking the movie tickets that we have pointed out in our functional requirement? Let's start with the first requirement for searching for a movie. We need a REST API here, GET API. So start with the right format for the REST API. So get REST API. For the search functionality, we have a search criteria. Let's say the name of the movie, which would be in this format. And we also need a language which user is providing as part of the search criteria. And there could be a many more optional fields here. This is the REST API. For the search, it would have a response. The response would be the list of movies and it would look like movie, which is an of movies. Each element in the array would have the details about the movie like ID, name. So this we should be able to clearly explain. Now again, it depends which direction interviewer is looking for you to get into the detail. You may skip this and can just say that this is your GET API, but this I would highly recommend you to at least mention this. This is must needed for your interface. This is an optional that you need to judge where interviewer is looking for you to explain what is the actual response of this GET API. Next is the GET API again for your getting the movie details. So movie and the details for this movie you can mention with this query parameter. This would be your GET API for getting the movie details. The response here would be the detail of the movie and the actual JSON here would look like as part of the movie. This would be actually like this, and each of these field will have the detail about the movie, and it would have a further few more metadata which is not there as part of the search functionality, where it will have a minimal information and here it will have the this API will have the detailed information for that specific movie. Okay, let me make some space here so that I can talk about our third requirement. We have satisfied the first requirement for the search for getting the movie details. Now the third requirement is for a book ticket. Now this would be your third API for booking movie ticket, and this would be the post API. So let me make some more space here. Okay, let's talk about our third API, which is post API, and this would have a movie ticket booking. The request is more important here. So if you see in the GET API, we have discussed in detail about the response of those API. But in case of post, the request is very important, that what parameters are we actually passing for the post. Now if you see, if you wanted to book the ticket, what information do you want to pass to this API so that you would be able to book the movie tickets? You need user ID. Let's say we have 1, 2, 3 user ID. in the request, and you need the movie ID, which is 456. Now you would understand here that when you're trying to book a movie, that we have not figured it out while doing the schema design, that when we try to book a movie, we wanted to book into a specific theater. For such functionality, so far so good. We get the list of the movies, we get the detail of the movie, but we also interested to see the cinema or theater in our city where this movie is launched. So now you see this particular requirement we have missed when we were discussing about the core functional requirement, that we might need to search by the cinema theater as well. That's completely fine because we wanted to start with something simple based on our understanding, and as we go forward we can keep on adding these requirements as and we encountered or identify during our discussion. So now let's think about the scenario when we are searching for a movie and we are selecting a cinema, and after selecting for a movie there would be a show. For a simplicity, let's say our shows are like from 12 to 3, 3 to 6, 6 to 9. There are 3 and 4 shows are there per day. User can select particular show. So movie theater will have the list of seats, and in the theater any movie would be launched. So when user would search, get the list of movies, user will select a particular show, and that particular show will have the theater ID and how many seats are there in that particular show. Now in the theater the seats are having a limited inventory. For example, in particular theater the first row contains the 10 seats for the row number A, and if multiple users are trying to book the same seat, we need to have these data exist into our database into the representational format, as in for a particular day, let's say for tomorrow we have so and so theater where there are these many seats are there, and let's say there are 10 seats are there for a show between 12 to 3, 10 seats are there for 3 to 6. Now user can book 5 seats on show 1 and user B can book 7 seats on show 2. So now you would see that only the movie for your core entities are not enough. So let's add few more entities here based on our requirement, what we identified as part of our API design. Okay, let me try to add more core entities that we have figured out that we need as part of the post API, that we must have the theater where this movie is launched, and for each theater as well there would be a shows because the same seats would be there. Let's say there are 10 seats in the theater, so let's start with the theater first. This theater, let's say this theater will have the ID, name of the theater, address of the theater, and let's say it has the list of seats. Now how does this seats are look like? Okay, so let's have this seat also as one entity. How does this seat looks like? Seat would have multiple rows, and the rows will be numbered as A, B, C, D, and there will be a column. This is the list of seats in a particular row, that could be mentioned as 1, 2, 3 to 9 or 10. Like if we have a 10 seats per row, and let's say we have these many rows. So this is our seat table and this is our theater table. Along with that we also need a show table here. So now the show would have the show ID, it will have the start time and end time of the show. For this particular date, for today, the show start from 12 a.m. to 3 a.m. or p.m., 3 p.m. to 6 p.m. for today. For tomorrow, there would be another show where all these 10 seats from that particular theater will be available for different date and different time. Each show will have a theater ID and the movie ID. So if you try to do the mapping of these core entities into our system, so you would see here in this system, right, for these entities, you would see here that these shows will have the number of seats. Let's say this show has 10 seat for a simplicity. For every show has a 10 seat, like for a particular date, 3 to 6 p.m. and then 6 to 9 p.m. again it has a 10 seat. And these show IDs are mapped with the theater ID and the movie ID, which is a foreign key. This theater ID is a foreign key for this show table, which is the primary key of the theater table. Similarly, this movie ID is a foreign key of this show table, and the same movie ID is the primary key for the movie table. So this is how we are thinking in terms of the relational SQL tables. And for a particular theater, when user is trying to book, so each theater, each show will have a one theater ID mapped to it and one movie ID mapped to it. And this is how there will be a list of shows for a particular date, and there will be a list of seats. Each seat we can have a status as well for each seat, like whether this is booked, available, or reserved that we wanted to see as a more reserve concept in our deep dive. But this is how, for a simplicity, we are thinking about these tables, and these are the core entities and the attributes that we wanted to expose. So we can have these seats available into our database into a representational format. Let's say for next 3 days, if we are allowing to book a seat or book a ticket for a particular movie, so we can run a batch job overnight which can create the records in our database. So let's say for today's date, right, it creates these many records based on the seats, available seat for a particular theater. So these data, all the status of each of these seats would be initially available, right? And as and when user are trying to book, status will be changed to a booked status. So this is called a database representational format already exists into the storage. As we have seen, the storage are not very high, so we can keep on creating the storage into our database and will allow these records. We need to expose these data to our user. So as of now, you have seen that we have started with very simple requirement for searching for a movie. We discussed about the cap theorem. We are explaining to the interviewer that there is something in back of our mind about the scalability of the system, the performance of the system, and we have done some calculations. We are created the core entities of the system, which we are exposing through these APIs. So we have talked about enough technically that how we wanted to have our system. But let's get into the high level system design, that how does the end-to-end flow would look like. Now we need to connect these bits and pieces and give a picture about the end-to-end flow for our proposed solution. So let's get into a high level system design. This is the step 5 for high level system design, where generally we wanted to start with something very simple, that what we have in our system and how do we wanted to expose this data to our users. So let's start with simple client. This client can interact with this service, and we have a database. We are not making any choice whether we want to use SQL, Postgres. It's something that we are mentioning that we are using a relational database, and the joins, the queries, what we have discussed, that is provided by most of these vendors on the relational database side of. Okay, so now this client can make REST API call for this service, and this service can fetch the detail from the database what we have discussed. So this we are starting step by step with a very simple high level, and then we want to make sure that the complete functionality works end to end. This client could be or it could be an Android, or it could be iOS, right? And this is how this client is making use of the API what we have exposed. Like for search API, we have exposed to search for a movie. We have exposed another API for view detail API, another API what we have exposed as book ticket booking API. So here we are mentioning that this would be our Spring Boot service or any other service which has exposed these endpoints for our core functionality to get the availability of the movie for a particular show that we have discussed. In like here we have discussed about the theater, the show, movie, user, and seats. So these schemas, right, these core entities are exposed by these database, and this API is gonna query this table and return the result to the client. But as we know, this is not a scalable system. So one single service would not be able to serve the request like what we have seen as part of our non-functional requirement, that we need thousands of requests for search, right? And then we need like for ticket booking as well, thousands of requests per second we need for ticket booking in case of peak season. Considering this, we need to have our scalable system. Also, we haven't talked about here the authentication and authorization. We do not want this service to do the authentication and authorizations, rate limiting. So this is also something that we need to consider as part of the system design. So let's elaborate this simple high level system design. And as I discussed with my previous step-by-step approach for the system design, this is the area where from SDs to senior software engineer would like to focus more on completing the end-to-end functionalities. However, for the staff to principal software engineers, as I mentioned, this part we should be able to complete in 2 to 5 minutes to just give you the overall picture that whatever you have discussed here, how this functionality would work end to end. It is not just throwing the random APIs or the schemas. Right now here we are connecting the dots, like whatever we have proposed, how it's gonna work. So let's start adding the API gateway onto this system. Before that, let me move this little here. This is the API gateway. You can mention that what all the functionalities that you wanted to leverage from the API gateway. For example, if we have a microservices, which we haven't talked about it, but still I would suggest you to mention here and move forward, because we may not get time to come back to the API gateway. We wanted to have the load balancing from the API gateway or the routing. We want the authentication, authorization. Also, we wanted to leverage the rate limiting. So you are using the in-house API gateway or the cloud API gateway. These are the parameters you can configure in your API gateway. While mentioning these features, you can mention like here itself, like rate limiting. You wanted to do the rate limiting for each of your API which is being exposed from this service, so that any malicious users cannot attack your service to make the system down. So for a particular user or IP address, you can have the number of requests that can you are allowed for per second. Like let's say you are allowing 5 requests per second for a particular IP address. How you are gonna have the authentication and authorizations as part of your API gateway? Are you gonna have a two-factor authentications? Routing is something like if you are having a multiple services like that we will see soon for a search functionality and for a booking functionality. If you have a multiple services, how the request is being routed through a different microservices from the single API gate. And if we are having a multiple instances of the same services, how the load balancing can be done on the round and robin fashion. That means like one by one calling a different instances of the services, or whether you wanted to have based on the CPU or RAM performances or the load on the server, which request you wanted to redirect it to which server. So this is a API gateway. That is the first user facing APIs for your client. So client will have to go through these functionalities from this API gateway. And now what we want is we wanted to scale the system for a separate service for a search. So we have one service, let's say this is just search service, and this search service is a kind of a reach path for our system that can scale on its own. 100 million daily active users can search every day, but out of that we have discussed only 1% of the users are trying to actually see the movie details or trying to book a ticket. So that's how we can have a different service for that specific purpose, so that both of this service can scale on its own. So this is a search service, and let's say this is a movie service. Now, movie service would provide the functionalities for detail and ticket booking, because this is what like not every user gonna do. And the search service, let's say this provides exposes a single API search. This relational database here, these movies is being added. Now we can talk about that. Here the admins are adding, removing the movies here, adding movie from so and so date or update movie, and we do not want to get into the detail for the admin, as we are assuming that in our relational database the movies are there into our system when admins are adding into our system. So this relational table will have the list of movies. So let's first focus on the search functionality for the system. So let's say user are making a search query to this service. This service is going into the database and doing the search of the movies. But now we can see that this search for a relational table would be a redundant, right? Like let's say for a particular city, everyone, like thousands of people are trying to do the same search, and the same search query is being performed into the database. So we wanted to optimize this. We probably can use the Redis cache here, so that whenever any search performed, we can store in-memory data structure on Redis. So this service, instead of going again and again to the database, it can go for the first time for searching for the movie, and we can have some TTL here for a day, let's say, right? Not every day or every hours movies are being added into the system. So theaters are being added to the system for a particular day. For that particular TTL, for the first time when the query is performed, we can save into the Redis cache, and from then onwards, the same search query, if you are getting again and again, we can directly go to the Redis in-memory cache and we can return the request to the user. So this is the search functionality what we have optimized. We can also talk about the multiple instances of this search service. The load balancer will go onto a different database. We can talk about the partitioning of the database as well, but let's not touch upon the partitioning at this point of time, because we know that the data is not too much and that can fit into a single instance. Probably we can have a read replica. So instead of partitioning the database, we can have the read replica, and anyways we are using the Redis cache here. So distributed Redis cache also we can talk about. If required, we can have the distributed multiple cluster of Redis cache based on the hashing of this. So these are the points probably you can just mention when you are going through. But I would suggest you and highly recommend you to focus on the core functionality. If you're trying to scale the system, what services you are trying to leverage, how you're trying to leverage this cache to scale the system. So this is the usage of the cache through the load balancer API gateway. We are redirecting to a particular service. Now, after searching, we wanted to see the availability of the seats for a particular theater. So user will go onto this movie service, and this movie service can query the database to get the multiple replicas are there. So it can query the relational database to get the availability for a particular show, for a particular theater and movie, and return the availability so that user can call the ticket booking API and can book the tickets here. So far so good. We have covered here the looking at details of the movie, ticket booking. Now here we wanted to touch upon the important topic. We wanted to talk about the concurrency of the system. So if multiple people are trying to book the same seat, how this gonna work, how we wanted to handle that scenario. And in fact, this is a key functionality or the part of the deep dive where interviewer might want you to get into the detail and show your technical skills. So these are the database concepts are there. Probably I will create a separate video for going through detail about each of these concurrency concept on the database, how this problem is being handled. But right now, as part of this problem statement, we wanted to use the distributed log. So that is the better solution for reserving the ticket. Let's say if user A is trying to book a ticket, if is in the user A is in the payment state and user A does the payment successfully so that the ticket is booked. But when user is trying to complete the payment, that is a window of, let's say it takes 2 minutes or 3 minutes of time for user A to complete. And at the same time, if user B is coming and trying to book the same ticket, so that should be seen to the user that this particular seat is currently blocked or reserved. And if user A completes the payment, that particular seat is booked forever. But let's say for some reason the payment did not get through successfully, we wanted to unblock that seat so that for user B or user C, if they come after, let's say 10 minutes and user has not booked the ticket successfully, that should show a user B or user C that ticket is available for them. So what we can do here is, when this service is going and querying to this database for the availability of the seat, let's say the particular seat is available and it is giving the result to user A, it can put a TTL to this Redis. Let's say 10 minutes for this particular seat is logged by a user. And if user A completed the payment, we can put the permanent status here. In this, at this point of time, in this point of time before completing the successful payment, the status here is available, but it is reserved here, right? So user B is trying to search for same ticket. User B first searches on the Redis cache. In Redis cache, it is searched, it is looked as reserved, so it shows as a particular seat is blocked to user B or user C, right? Now for some reason for user A, that the payment did not go through successfully, but the seat is still available, right? After 10 minutes, after the TTL, this entries will be removed from the Redis lock, Redis cache. And if user B tried to search, user C, it is available here, but it is not, the entry does not exist here. So the seat will be available to user B. So for this purpose, we are using a centralized Redis lock. Why we are calling it a distributed lock here? There could be multiple instances of the database. And before querying to the multiple instances, user B or user C can always see to this particular central lock whether this particular ticket is reserved or not. So this is a one mechanism for the distributed lock that is useful for this particular problem. But there are some scenarios where the two-phase commit is used. For some scenarios, optimistic or pessimistic lock is used. These is handled at the database level, pessimistic and optimistic lock. Distributed lock is handled at the in-memory cache level. Database level, it means like if user A try to book, reserve a ticket, it can put a lock at a particular row at a database level, and the lock can be released. There is a shared lock, right, or exclusive lock that I will explain in detail in a separate video. But for this particular problem statement, we are using the distributed lock to handle the concurrency issue. This is how only one ticket will be booked globally if thousands of users are trying to book even a single seat. Okay, another area of improvement we can think about, as we have handled the search functionality in the Redis cache, we can also use the CDN here. CDN is geographically located, and generally in CDN the static data is being used. For example, let's say the movies is having the, let's say it is having the images, photos, trailers. So that can be put into the CDN link. That client can directly query the CDN nearby link to query and see the trailer for that movie. But also, what we are trying to focus on a search and booking functionality, the query that also is considered as a static. This query can also be added into the CDN link along with the Redis link. Since this CDN link will be closer to the user geographically, so user can query the CDN link for the API request and can get the response from the CDN link as well before going to all the details into the cache and database. So for this purpose, CDN also can be used. So now we have handled the search, scalability, relational table, Redis lock. Before I complete this end-to-end deep dive, I wanted to point out, I see many candidates use different databases. Like I have just considered here the relational SQL database here, but some candidate also, you can also consider like Cassandra, MongoDB, a different database for search functionality, different database for a booking functionality. Probably this you can use a MongoDB, which is in representational format for JSON, how you wanted to show the list of movies, and here you can use the SQL DB for the booking functionality. But if you try to use a multiple databases, different databases, you need to be very careful on making those decisions. Are that is really gonna help you, or will it be overhead for you to maintain, for the maintenance of these different databases, right? So it's decision whether we need a single instances or single vendor databases or multiple choices from a database from a multiple vendors. So that is something that need to be looked carefully if you are making those decisions. I would strongly recommend to go with the simplicity and try to have a single vendor database for particular this use case, and handle with a caching and CDN link mechanism for your performance reasons. At this point of time, we have covered the step number 6, which is deep dive, and mostly you should be able to cover around 40 to 45 minutes by now. And before we close this, and in fact, if you are near to your end time of your interview, interviewer might ask you, do you want to add anything on your system design? Or if you have some time, you can take 2 minutes to talk about the operational excellency for your system. You wanted to start with logging. So since you are having multiple services here, API gateways, different services, so you wanted to track the request once the user has created the request, which stage your request is, which service the request is going. So you need to have your logging. Probably you can suggest that based on your expertise level, you can suggest like Splunk you can use for logging here. Monitoring is something critical to consider in every system design. So you can suggest a Grafana for monitoring dashboard, and Prometheus for periodically getting the performance of the servers, the CPU utilization, RAM utilization, and checking. Now that is the next for checking the alert. You can say that you are using a PagerDuty profile. You can set the alerts in the Splunk logs. You can configure if there are 10 errors within 3 seconds, you wanted to raise this alert. Now this alert can raise a PagerDuty that can send an email or make a call or send an SMS to the developer or the production support team to check what is the issue with your service and act on it by restarting it or by rolling back the latest version to the previous version. So these are the operational excellency that you must talk about as part of your system design interview, almost at the end of the interview, to give a sense of the ownership and the responsibility that you take when you drive the requirement from end to end, right from requirement gathering, how you basically gather the requirement, what are the non-functional requirement that you can think about it before jumping into the technicals of it, right? And then start with the schema design. That is a step number 3, where you would see what is the actual data, right? How do you want it to store, what is the relationship? And that is perfectly fine if you start with something simple and come back to this to add more details to it as and when you identified. Then how this data will be exposed to the user. What kind of a API do you need? Do you need the REST API? Do you need the webhooks, long polling, short polling? What are the user interface APIs? How the request and response would look like? Once you talk about that, then you go with the simple high-level system design with the 3-tier architecture. That is a step number 5. This is a step number 6, where you go into deep dive for scaling of your system and showing your actual technical in-depth skills. And while explaining each of these block diagram, you need to keep on giving the features and what all the knowledge you have, for example the API gateway. Now we do not have time to come back to this, like how we wanted to do all that, right? Once you added the API, you add then and there itself what are the functionality you wanted to use it, because this is a part where we also wanted to consider, like before our interview is completed, we wanted to talk about the operational excellency as well. So I hope you would have learned something today, how you wanted to drive your system design interview, how you keep making a note of the time based on your seniority level, how you can follow this 7-step approach for any topic. Today we have considered the ticket booking topic here, where we have talked about all this step by step approach that you should be able to cover within 45 minutes to 60 minutes. I will be creating more such videos covering as many as different topics I can, which is being generally asked in the interviewer. Similar to this ticket booking system, there are many more such interesting topics are there. Check out my more such videos to getting the in-depth knowledge of many more interesting problems. Till then, goodbye, enjoy learning. Thank you.